All right, I'm going to continue with the series on elastic collision analysis videos. This is going to be number 8. So again, the point of this series is to prove two things. And one thing is that within the context of conservation of momentum, that momentum is a vector, which means that if after collision, if both cars move in the same direction, then you would have to add those momentums together in order to get the same total initial momentum before the collision. So the initial total momentum that went in before collision. And if, however, after collision, one of the cars goes in opposite direction, right? That means that you would have to subtract both momentums in order to get the total initial momentum that went into the system before collision, right? That's one thing. And then the next thing is to prove that this equation here, right, that predicts the velocities after collision is in fact a reliable equation, that it works. Okay. So those are the two things. So we're going to look at this experiment here. So this person is using a Pasco, a Pasco set, experimental set of Pasco. Okay, we have a blue card and a red card, and they always, now even though he does not weigh those cards, he does not put them on a scale, they have a standard mass. They have standard masses. In every single video where they use Pasco cards, they always have the same weights. It's 250 grams each. The blue card and the red card weigh 250 grams, and then you can add extra masses onto it, these little bars, and they each also weigh 250 grams. Okay, so we can be pretty sure what the weights are, even though he does not say the numbers and he does not weigh them. They are standard weights everywhere, all over the world. So he does two experiments. He does 200, well, he lets a two mass collide into a one mass and a one mass collide into a two mass. And we're going to check both of them and see whether or not the equation that predicts the velocities after collision is correct or not, and whether or not momentum is conserved. So first he will start with letting the two mass, the 500 gram, collide against the 250 gram.
Much friction. And so let's give this a push again. Boom.
All right, so that's it. The velocity of the blue card was 0.49 meters per second. So his PhotoGates, well, his software immediately calculates the velocities. So we have an incoming velocity of 0.49 meters per second, and the red card came out with 0.62 meters per second. Now the blue card will continue to go into the same direction.
0.49, and then the head barely made it.
And the blue card comes out of the second PhotoGate with a velocity of 0.07 meters per second. But of course, it was a long distance. It needed to travel a longer distance to reach the second PhotoGate, and it lost quite a substantial amount of velocity, even though it's a low friction metal track. If the velocities are low, it will still deal with quite a lot of friction, and thereby its momentum will be a lot less. So let me show you again.
Okay, so I get the most active 9.
So you can see the blue card took a couple of the blue card took a couple of seconds to go through the second PhotoGate. All right, needed to travel a long distance, and its velocity slowed and slowed and slowed, thereby losing a lot of momentum. So the velocity of the blue card entering the second PhotoGate will be quite an inaccurate result. So I have done the calculations. This is the two mass versus the one mass. So these are the measured results. The incoming velocity of cart 1 is 0.49 meters per second. All right, and the red cart came out with a velocity of 0.62 meters per second. Now the prediction was, okay, for the red cart, for the one mass, the prediction was 0.65 meters per second. And it came out with a velocity, with a measured velocity of 0.62 meters per second. So it's a really close, they are really close results, okay? So 0.65 versus 0.62, a really great match. Now, the blue cart after collision should continue to move with a velocity, with a predicted velocity of 0.16 meters per second, but the measured velocity was 0.07 meters per second. But again, the distance, it took a long time before it went through the second photo gate. It needed to travel a lot of distance, and thereby its velocity has slowed down a lot. And therefore it had lost quite a substantial amount of momentum and velocity. So that would mean that the conservation of momentum is not going to be that great because of the lots of loss of velocity. The initial amount of momentum is 0.245 kilograms times meters per second. And then the red cart came out with a momentum of 0.155 kilograms times meters per second. All right, and then the blue cart continued to move with a momentum of 0.035 kilograms per times meters per second. If you add these together, you only get 190, and the initial momentum was 0.245. Again, I blame it. The friction is to blame because of the blue cart losing a lot of velocity since it has to travel so much distance to enter second photo gate. All right, now we are more interested in, well, first of all, the predicted velocity 0.65 meters per second and the measured result 0.62 meters per second is a great similarity. It's a great approximation. So again, this would prove that this equation is reliable. So now for the second case, the other way around, the one mass colliding against the two mass. Let's take a look.
So when the blue car was going through a point before the blue car
races. This is it. No. It needs to be the other way around. Let's see.
A little bit.
Okay, he's going to change the weights.
Over to the red car. Okay, so now the red car is 2 mass units. And the blue car is 1 mass unit. So now I'm going to push that through. What do you think is going to happen? Light car, heavy car. Opposite of what we just did. Well, that's why I set it up. Let's find out. All right, so let's give this a push.
All right, so the initial velocity, hold on.
Well, that's why I set it up. Let's find out. All right, so let's give this a push.
Yeah. Okay, so the initial velocity is 0.69 meters per second, and the red card came out with velocity of 0.43 meters per second. And then the recoil, the reflection, is 0.16 meters per second. Great, so velocity 1.69 meters per second. Okay, so the prediction for the two mass is that it would come out with 0.46 meters per second with this, using this equation, and the measured velocity is 0.43 meters per second. So 0.43 versus 0.46, a great approximation, really close results. Okay. Once again, so this formula is quite reliable. And now again, so for the reflection, the prediction would be 0.23 meters per second, and the measured result was 0.16 meters per second. Again, problem is we're still dealing with a track that, even though it's a low friction track, there still is friction at play, and the slower the velocity, the more friction there will be, and the more momentum is going to lose. Well, the more velocity it's going to lose, especially. And so this is why there is always going to be a bigger difference for the reflection, because it's moving slower. Now, okay, so let's take a look at the momentum. So we have 0.69 times, so the initial velocity 0.69 meters per second times 0.250 kilograms, which is 0.172 kilograms times meters per second. So this is the total amount of initial momentum. After collision, the two mass has a momentum of 0.43 times 0.500 kilograms, which is 0.215 kilograms times meters per second. Okay, and the reflection of part one of the one mass is 0.16 times 0.250, which is 0.040 kilograms times meters per second. All right, so one mass went in opposite direction after collisions. So theoretically, according to conventional science, we have to subtract those momentums. If we do that, all right, 0.215 minus 0.040, then we get a result of 0.175. So 0.175, and the initial amount of momentum was 0.172. So really close. 172 versus 175. Really close. If we subtract them, it's really close to the initial amount of momentum. However, let's compare models again. According to Draftstein's model, the momentum is treated like a scalar, so it doesn't, the direction does not matter. We have to add momentum always, doesn't matter what happens. If we do that, if we add if we add momentums after collision together, so 215 plus 0.040, then we have 0.255. 0.255 as an end result, even though the initial amount of momentum was 0.172, which means we have gained a lot of free momentum. Once again, in a new kind of experiment. So for the kinetic energy, if we take a look at kinetic energy, the total initial amount of kinetic energy was 0.0595 joules. After collision, the two mass has a kinetic energy of 0.0462 joules, and the reflection of part one of the one mass has an energy of 0.0032 joules. If we add those together, right, because kinetic energy is a scalar, then we have 0.0494, and the total initial amount of energy was 0.0595. So we have lost about 100 joules, and it does make sense that we have lost energy. Okay, whereas if we consider momentum to be energy, then we have gained energy, and that should not be possible. And that's not what happened. There has no free energy was created at all. Is again, the main point once again is that there is this conflict between momentum being a vector or a scalar. I have now, this is the 8th video in a row that proves that momentum can only be conserved, okay, if it is being treated as a vector, if the opposite direction is treated as a negative value. If we do not do that, if we treat it as a positive value, then we always end up with free extra momentum. Okay, and this is once again, this person who's doing this experiment is once again an independent person, right? Somebody else somewhere in the world doing this test. Okay, and he's getting the same results in the sense that, okay, that momentum can only be conserved if we subtract both momentums after collision. Again, draft science would say that this person has deliberately manipulated this experiment to come out the way of kinetic energy. I would say, no, come on, this is ridiculous. All these independent people doing these experiments would somehow all secretly change their setups, trying to make it force coming out the way of kinetic energy. That's absolutely ridiculous. That's the perfect description of a conspiracy theory. So this is another piece of evidence to throw into the pool of evidence. So okay, I'm going to put the link of this experiment in the description box. I think that's all. Up to the next analysis video.